Good day, everyone. Our topic for today will revolve around Eulerian and Hamiltonian paths and circuits in operations research. Here are the main points to talk about in this presentation. First, we have graph theory. Then, we have the components of a graph, which will be essential in understanding our topic. Next, we have paths and circuits, Euler paths and circuits, and lastly, Hamiltonian paths and circuits. Just a quick background of graph theory. Graph theory refers to a branch of mathematics that deals with the mathematical diagram or representation of a network of points called vertices connected by lines called edges, which constitute a graph. Graph theory originated in the 1700s as a solution proposed by Leonhard Euler to a puzzle known as the Königsberg Bridge problem. Back in the 18th century, in the Prussian city of Königsberg, a river ran through the city, and seven bridges crossed the forks of the river. As a weekend amusement, townsfolk would see if they could find a route that would take them across every bridge without doubling back and return them to where they started. Leonhard Euler, being great as he was, solved the puzzle and said that it would be impossible to do such a thing by simplifying and representing the problem through graphs as shown below. Later, we will discuss the concept applied to this scenario. What used to be a theory to answer recreational math problems now has played significant role in our daily lives. Here are some of the fields where graph theory can be applied. First, we have graph theory, used in modeling chemical phenomena in chemistry. Second, we have genetics under the field of biology, DNA and RNA structure. We also use graph theory in computer science to develop algorithms for different problem solving. Lastly, we have operations research, where graph theory is used for transportation problems to maximize cost efficiency. This is where we will apply Eulerian and Hamiltonian circuits as we move on. Basic terminologies used in graph theory. Graph, as stated earlier, consists of a network of points connected by a set of lines. Next, vertex, which is the dot in the graph. It can represent different things such as intersection of streets, landmass, or a general location like someone's home, school, or work. Edges are the lines that connect pairs of vertices. They can represent streets or routes connecting two locations. An example of a graph. Another important concept is the degree of a vertex, which refers to the number of edges meeting at a particular vertex. Here we have 0 since there's no edge attached to it. Then here we have a degree 3 since there are 3 edges meeting on it. Then we have path. It is a sequence of vertices using the edges. In this, we are only interested in arriving from point A to M, no matter which edge we choose, as long as we get to point M, like the one shown below. There could be other paths as well for this example. On the other hand, circuit refers to a path that begins and ends with the same vertex as seen in the second graph below. Next, we have connected and disconnected graphs. A graph is connected if there is a path from any vertex to any other vertex. All the graphs we saw so far are connected. The graph below is disconnected. There is discontinuity between the left and the right vertices. Now, we move on to Eulerian and Hamiltonian paths and circuits. Leonhard Euler was a Swiss mathematician and physicist. He was arguably the best mathematician in the 18th century, contributing to geometry, calculus, trigonometry, number theory, and many more. He laid the foundation of graph theory by solving the Königsberg problem, introducing the concept of Eulerian graph. He said and proved that it is impossible for the residents to traverse all the bridges without backtracking. Here are some of the mathematical notations created by Euler. Euler path refers to a path that uses every edge of a graph without repeating a single edge. Given that it is a path, the endpoint of tracing does not have to be the starting vertex. In every graph, it is possible to have multiple Euler paths. Looking at our example, one such is from point C to B, E, C, D, E, A, and B. Same concept applies to Euler circuit. Euler circuit uses every edge in a graph without repeating a single edge. The only difference is that it must start and end at the same vertex since it is a circuit. In our example graph, we do trial and error to find an Euler circuit. There could be multiple Euler circuits as well, two of which starting with the vertex A are these. Now that we know what Euler paths and circuits are, how can we identify if a graph has one? First, a graph will contain an Euler path if it contains at most two vertices of odd degree. Second, a graph will contain an Euler circuit if all vertices of even degree. In our example, the Königsberg problem, Leonhard Euler used this concept to prove his theory. As seen in the graph, every vertex has an odd degree. North bank has 3, island has 5, east bank has 3, and south bank has 3. We conclude that this graph doesn't have an Euler circuit. Next, though it is possible to find the Euler circuit and Euler path using trial and error as we have seen, a more formal and organized method is Fleury's algorithm. The problem with trial and error is that having a more complex graph will make the process time-consuming. Here are the steps one must follow. But what if the graph doesn't have an Euler circuit? We can apply Eulerization, which is the process of duplicating edges of a graph to create an Euler circuit. Basically, we are duplicating edges of odd degree vertices so that it will become even. Here are the important things to consider. In Eulerization, we don't want to create a new edge because this, in real life for example, will suggest constructing a new road, which isn't practical and is costly. We will duplicate an existing edge, meaning that the people of Königsberg have no choice but to walk on some of the bridges twice. In addition, given the graph below, what we want to choose is the graph that has the least duplicated edges, which is either graph 1 or graph 2 for efficiency. Applying Fleury's algorithm on graph 1, we find that one possible circuit goes from SB to EB, NB, EB, I, SB, I, NB, I, and lastly SB. Moving on to Hamiltonian paths and circuits. Unlike Eulerian, Hamiltonian considers the vertex of a graph rather than the edge. To formally define, a Hamiltonian path visits every vertex once without repeating, but does not have to start and end at the same vertex. In the graph shown below, there can be multiple paths as well. One such path is from point A to B, E, C, and D. On the other hand, Hamiltonian circuit visits every vertex once without repeats and must start and end at the same vertex since it is a circuit. In our given graph below, there can be multiple circuits, but one such starting with vertex A is A, G, E, F, C, D, B, and A. Real-life application of Eulerian circuit. The given scenario is this. Say my birthday is coming soon, but unfortunately, due to the pandemic, I cannot have my friends in our subdivision to come over to our house. So, I thought of just distributing the food that we will prepare door to door to a part of our subdivision as shown below using Google Maps. Question. Is there an optimal route I can take that will allow me to save time? We translate the map into a graph, and we get this. To find the optimal route, we first determine if the graph has an Euler circuit. Since there are vertices that have an odd number degree, we conclude that it doesn't have one. Step 2. Given that it doesn't have an Euler circuit, we create one by Eulerization. Duplicating the edges of odd degree vertices, here are some possible graphs. Because we see that the first Eulerization has the least number of edges or backtrack, we take it as our optimal Euler graph. Lastly, we find the Euler circuit using Fleury's algorithm. Knowing that we can start at any vertex, we started at vertex A since it is closest to our house. We see that the optimal route using the concept of Eulerian circuit is this. Now, we ask ourselves, where can these concepts be used? In the modern world, it is essential that we find the most efficient way of doing work. This type of scenario can be applicable to operations research since it is a type of transportation problem that involves cost efficiency. Eulerian and Hamiltonian concepts will be helpful to people whose work requires them to traverse all edges or streets in a place, including but not limited to delivery guy, postal carrier, garbage collector, and police patrolling officer. Naturally, they will opt to choose the most optimal route where they can finish quicker but at a lower cost. That ends our presentation. Thank you for listening, and I hope you learned something new in our discussion.